In the previous part, we have introduced the Cauchy stress matrix, and we showed that the Cauchy stress matrix is a symmetric matrix, and thus all the properties of that we studied for symmetric matrices apply for the stress matrix. In particular, if I have a coordinate system in which the stress matrix has a general form, S11 or sigma 11, sigma 12, sigma 12, it's symmetric, sigma 22, which means this number is equal to this number. There is another coordinate system made out of the principal stresses directions, or the eigenvectors of the stress matrix. In this new coordinate system, and of course between this coordinate system and this coordinate system, there is a translation matrix Q. So in this new coordinate system, the stress matrix is diagonal, which means the off-diagonal components are equal to 0, and the values of the diagonal components are called the principal stresses. So sigma 1 and sigma 2 are the eigenvalues. Of the stress matrix, and E-1, E-2 are the eigenvectors. Now in this part, we are going to study stress measures or stress invariants. So basically, if I have a certain coordinate system where the stress has certain numbers, let's say 3, 4, 4, 2, in this coordinate system, in a different coordinate system, I will have the stress with different numbers. So I'm going to make these numbers up. Maybe this will be 4.5, 0, 0, 7.3. So looking at those numbers, okay, 7.3 might be too much. I'm going to just put 3.5, for example. So looking at these numbers, I've got 3, 2, 4, and looking at this number, I've got 4.5 and 3.5. I'm not able, now this is the same state of stress. It's just a different coordinate system. Now looking at those two matrices, I'm not able to say, okay, which one is more severe, which one is bigger, or which one is smaller. And so we are looking for numbers that are equal independent of the coordinate system. So I'm looking for a measure of stress that is independent of which coordinate system I use. And this is what I call stress invariants. These measures are called stress invariants. And the first measure is what we studied before, which is the first invariant of any matrix, which is the sum of the diagonal components, but I'm giving it a physical meaning. Sorry, let me just go back. The first invariant is related to the first invariant of a matrix. Now let's just recall. When M is a 3 by 3 matrix, the first invariant of M, which is we call also trace of M, is equal to the sum of the diagonal components. Now, this is for any general matrix. Now, if that matrix is a stress matrix and the stress is symmetric, then, and let's assume that sigma 1, sigma 2, and sigma 3 are the eigenvalues of sigma, and sigma ij denote the component of sigma, then the hydrostatic stress, which is one of the invariants of the stress matrix, is in fact the first invariant of sigma, which is the sum of the diagonal components divided by 3. And since the sum of the diagonal components is independent of the choice of the coordinate system, I can sum sigma 1 plus sigma 2 plus sigma 3 divided by 3, or I can sum the components in a general coordinate system, which are sigma 1 1, sigma 2 2, sigma 3 3 divided by 3. So whether I'm in this coordinate system and it's symmetric, so I'm not going to continue writing. So either I sum those and divide them by 3, or in the other coordinate system where I have only sigma 1 0 0, only the principal stresses, since the sum of the diagonals as we studied is the same, so I can basically sum those 3 and divide them by 3. And as we studied earlier, this is independent of the coordinate system, so that number is always the same. Whatever coordinate system you're working with, you're always going to get the same number. Now, this is just really simple problem. The stress at a point is represented by any of the following stress matrices. Find the value of the hydrostatic stress in each case. The hydrostatic stress in this case, P, is equal to 1 plus 2 plus 3 divided by 3. So 3 plus 3 is 6. 6 divided by 3 is equal to 2. Let's say this is units of MPa. So this is MPa. So the hydrostatic stress is 2 MPa, and in general it's a measure of the average normal stress on an element, because we're adding the 3 and then getting their average, and a positive value indicates an average stress of tension, and a negative value indicates an average stress of compression. P represents the average normal stress at a point, and positive indicates tension, while negative indicates compression. So the next measure, stress measure, that we are going to study is called the deviatoric stress tensor. And the deviatoric stress tensor is defined as follows. I will take my stress matrix and assume it's decomposed of two matrices that are added to each other. The first one is made out of P 0 0 0 P 0 0 0 P, where this is the hydrostatic stress that we calculated in the previous that we defined in the previous just right now, in addition to another stress matrix, and this other stress matrix I'm going to call the deviatoric stress matrix. This deviatoric stress matrix will also have to be symmetric, but I don't have to write it as a symmetric. I'm just going to write it. I'm just going to write it in its general form. And in a matrix equation, I'm going to write that the stress will be decomposed into a number P multiplied by the identity matrix plus another matrix which is called the deviatoric stress tensor. Therefore, this deviatoric stress tensor is equal to the stress matrix that I have minus Pi. So the deviatoric stress tensor is defined as sigma minus Pi. Now, why would I do something like this? Because it turns out for linear elastic materials, it turns out, as we will study it later, in constitutive models, that the deviatoric stress tensor is responsible for the shearing, deformation of materials. So this decomposition seems to be natural, because then I'm able to say, okay, well, this part of the stress is responsible for any shear deformation of the material, and this part of the stress tensor is responsible for any volume changes of the material, or shearing deformation, which basically means change of shape of the material, change of shape, or distortion. And we will study this later more in the constitutive laws. Now, what can I say about the trace, or the I1 of S, the first invariant of S? Let's see. I know that trace sigma, or I1 of sigma, the first invariant of sigma, is equal to sigma on 1 plus sigma 2 2 plus sigma 3 3. Now let's try to find trace S. Now this is the trace of sigma minus Pi, which is equal to sigma on 1 minus P plus sigma 2 2 minus P plus sigma 3 3 minus P. But I already studied that P is the average, or the hydrostatic stress, which is equal to, so I've got 3 P's. One of them, each one of them is equal to sigma on 1 plus sigma 2 2 plus sigma 3 3 divided by 3, which means that this is equal to 0. So if you're ever calculating a deviatoric stress tensor S, and then you take its first invariant, which is basically the sum of its the sum of its diagonal components, and you don't get a 0, then there's something wrong in what you've been doing. Another simple problem. I have 3 different matrices. I want to decompose each matrix into its deviatoric component and the hydrostatic stress component. I'm just going to do it for one of them. Let's take the first one. Units of MPa. P is the average stress, or the average normal stress. 3 plus 3 is 6 divided by 3 is 2 MPa. I'm going to decompose sigma into 2 0 0 0 2 0 0 0 2 plus whatever is left. So 2 plus something is equal to 1. So this is equal to -1. Let me just write the result here, which is equal to sigma. So 1, 0, 0, 0, 2, 0, 0, 0, 3. So 2 minus 1 is 1. 2 plus 0 is 2. 2 plus 1 is 3. So 0 plus 0 is 0. 0 plus 0 is 0, and so on. And so, or you could have calculated it simply by saying that S is equal to sigma minus pi, which is basically the stress tensor that's given, minus P, which is 2, multiplied by the identity matrix, and you'll get -1, 0, 0, 0, 0, 0, 0, 0, 1 units of MPa. So this is my S, and you can do this for the rest. And this is called the deviatoric stress tensor. So this is the hydrostatic. So sigma is equal to pi plus S. This is the hydrostatic stress component. And this is the deviatoric stress component. And it's very important to know, or to differentiate between P and I. P is a real number, it's just a number, while I is the identity matrix, that's a 3 by 3 matrix. So you really need to differentiate between the different variables. And of course S is a matrix. It's a 3 by 3 matrix. Another stress measure that's heavily used for the design of metals is what we call the von Mises stress. And the von Mises stress is an invariant of the deviatoric stress tensor. So when I take the deviatoric stress tensor and then I calculate its second invariant, and if the second invariant is given by this equation, visit the matrix invariance section to remember what this was. The von Mises stress is, we take that second invariant, which is independent of the coordinate system, and we multiply by -3, and we take the square root of -3 I2 of S, which happens to be equal to 3 over 2 I1 of SS. And the reason why it's equal to 3 over 2 I, because this part, the trace of S, which is equal to I1 of S, the first invariant of S, is equal to 0. If you go back, trace S, which is equal to the first invariant of S, just different names, happens to always be equal to 0. So this is always equal to 0, and so I'm left with I1 of SS, which in component form has this form. Now the von Mises stress can have a different you'll find different equations, and you can use any of those equations depending on the coordinate system that you're using. So let's say I'm using a coordinate system where the stress is already a diagonal. Pi is equal to sigma 1 plus sigma 2 plus sigma 3 over 3, 0, 0, 0, sigma 1 plus sigma 2 plus sigma 3 over 3, 0, 0, 0, sigma 1 plus sigma 2 plus sigma 3 over 3. And S is equal to sigma 1 minus P, sigma 2 minus P, sigma 3 minus P. The von Mises stress in this case, which is equal to the square root of 3 over 2, the sum I j equal 1 to 3 Sij, Sij. If I put this the components of S into this equation, I will get the famous formula. And you should verify it if you're curious to see how these two are related. If I have a general coordinate system, so in a general coordinate system, the stress has this form. And it's symmetric. Pi is equal to P 0, 0, 0 P 0, 0, 0 P, where P is the average, S is equal to sigma 1 1 minus P, sigma 1 2, sigma 1 3, sigma 2 2 minus P, sigma 2 3, sigma 3 3 minus P. The von Mises stress in this case, which is equal to the square root of 3 over 2, the sum when ij equal 1 to 3, Sij, Sij, which is basically S11 multiplied by S11 plus S12 multiplied by S12 and so on. This, if you substitute all of the above in here, you'll get the formula that you should never forget. Which is basically this formula. The von Mises stress is invariant, which means whatever coordinate system you're using, you should get the same number. Some notes on the von Mises stress. The first thing is the von Mises stress is termed the equivalent stress. So if I have a three-dimensional state of stress, sigma is equal to 9 numbers. The von Mises stress will take those 9 numbers and give me one number, and this one number I term the equivalent stress. It just gives me a measure of this stress. The higher this number, the higher the state of stress. The lower this number, the lower the state of stress. A few other notes on that von Mises stress is what happens if I'm in a uniaxial state of stress. So in a uniaxial state of stress, sigma, in this case it has sigma on 1 and the rest are zeros. The von Mises stress, in this case, if you substitute into your equation, you will get sigma on 1 squared plus sigma on 1 squared divided by 2, which is equal to the absolute value of sigma on 1. And this is very important because it takes the absolute value, which means the von Mises stress is equal whether sigma on 1 is tension or compression. And this is fine for metals and for some material. For other materials, it's not really, it's a bad measure. So this measure is good if the material does not differentiate between tension and compression, its behavior is the same. But for other materials where when you apply tensile stress is different from applying compressive stress, this measure would be bad. Which means that if I take a piece of material and apply sigma on 1, and if I take the same material and apply sigma on 1 in compression, so von Mises stress is the same, or in other words, they both states have the same equivalent stress. Just another problem just to show what I mean by equivalence of states of stress. As you see here, you've got two stress matrices. One has 2, 2, 2, 5, negative 5. Another one has 1, negative 5, 6. If you're not careful and you look at the numbers, you might say, oh, this state is higher because I have 6 here, but I don't have any 6s here. Or you can think that this is smaller because I have more numbers here than here. But in fact, both states are equivalent. If you take the hydrostatic stress, 2 plus 5 minus 5 divided by 3, you get 2 over 3, and let's say units of MPa. So this is for state of stress 1. For the second state of stress 2, 1 minus 5 plus 6 divided by 2 would also equal to, divided by 3 also equal to 2 over 3 MPa. The von Mises stress, which is equal to a big equation, substitute the numbers into the equation and divide by 2, you get the square root of 91. Similarly here, von Mises. Now this is a smaller equation because I only have the principal stresses. This will be equal to 1 minus 5 squared. I remember this equation because it's easier to remember. In fact, I remember both equations, but I'm just not gonna. It's simple, just look into the equation and substitute. 1 minus 5 squared plus 1 minus 6 squared plus negative 5 negative 6 squared divided by 2, you'll get the same number. Basically, we're saying that you cannot just simply look at the numbers in the stress matrix and say, oh, this one is bigger than the other, or this one is smaller than the other. You have to resort back to the stress invariants and look at the invariants of the stress, see are they equal or not. And in this case, both invariants are equal. How to calculate the von Mises stress using Mathematica. The next problem shows how to calculate the von Mises stress using Mathematica, and we'll present this in a different tutorial on how to use Mathematica. In the next problem, we find the von Mises stress in a general plane state of stress. A general plane state of stress is, I'm going to draw a cube and show you what a general state of stress is. If I have a cube if I have a cube inside a continuum, a general plane state of stress means I only have sigma on 1 and sigma on 2. Sigma on 2 and sigma 2, 2. The rest are equal to 0. Of course, they're the same values on the other side. So in this particular case, the stress matrix has this form. And the von Mises stress, if you look at the big equation that we introduced in a general coordinate system, sigma on 1 minus sigma 2 2 squared plus sigma on 1 squared plus sigma 2 2 squared plus 6 sigma 1 2 squared. And you can further simplify this equation if you prefer. So far we have studied the hydrostatic stress, the deviatoric stress and its second invariant, or the von Mises stress. The next section is the study of the maximum shear stress. And what is the maximum shear stress? Sometimes, for some materials, I'm very interested in planes So this is a continuum. I have stresses applied to it. I'm very interested in planes that have the highest shear stress. Planes in which I'm trying to distort or to slide the material on top of each other. For example, if I have a load P here, I'm basically interested in planes like this where I'm trying to slide the material on top of each other, simply because maybe this material is weak when I try to shear it. And so in a general coordinate system, when I have a stress matrix that's equal to sigma on 1, sigma on 2, sigma on 3, I'm interested, so this is a general state of stress where I have a point with all these stresses. I'm interested in the plane, the orientation of the plane that will give me the maximum sigma 1, 2 or sigma 1, 3 component. I'm interested in which orientation would give me the maximum value of that shear stress. So, as we will study the proof of this, the maximum shear stress is in fact related to the eigenvalues or the principal stresses of sigma. The maximum shear stress, so I'm going to call it the maximum sigma ij, where I is not equal to j, so the maximum sigma 1 2 or sigma 1 3 or sigma 2 3, the maximum number is equal to the maximum of sigma, the average or the absolute value of the difference between sigma 1 minus sigma 2 or sigma 1 minus sigma 3 or sigma 2 minus sigma 3 divided by 2. So example, if I have a state of stress where sigma 1 is 5, sigma 2 is 3, and sigma 3, for example, is negative 2, all in MPa, then the maximum shear stress is equal to the maximum of the following number: 5 minus 3, 5 minus negative 2, 3 minus negative 2, all divided by 2. So what's the maximum? 5 minus 3 is 2. 5 minus minus 2 is 7. 3 minus minus 2 is 5. So the maximum is 7. So 7 over 2. So the maximum shear stress is 3.5 MPa. So where is the orientation of that maximum shear stress? On which plane? Now you probably studied this when you studied the Mohr circle, but let's revisit how you calculate this orientation. And we're going to start from a coordinate system in which the stress matrix is already diagonal. What does it mean that the stress matrix is already diagonal? It means I only have sigma 1. This is 0. This is 0. And this is sigma 2. And it's the same on the opposite directions. I'm looking for the orientation where I'm going to call this sigma prime 1, 1, sigma prime 1, 2. I'm looking for the orientation with the maximum shear stress, where this number is the highest. So if this is the orientation, for example, of E-1. This is a new orientation, and let's say this angle is theta. This angle is theta, then this new orientation is described by a matrix Q, where Q is E-1 dot E1, E-1 dot E2, E-2 dot E1, E-2 dot E2, and revisit this section if you don't remember how to change coordinates. And of course E-1 is equal to cosine theta. Well, just gonna write it here. Recall. E-1 is equal to cosine theta E1 plus sine theta E2, and E-2 is equal to negative sine theta E1 plus cosine theta E2. So this is equal to cosine theta, sine theta, negative sine theta, cosine theta. So between this coordinate system and the new coordinate system, the matrix of stresses in the new coordinate system is equal to Q sigma Q transpose, cosine sine, negative sine cosine. Sigma is equal to sigma 1, 0, 0 sigma 2. Q transpose is equal to C negative S, S, C. When you do this calculation, you're going to find that the stress in the new coordinate system will have the following form. Don't forget, sigma here is equal to sigma 1, 0, 0, sigma 2, 0. Sigma dash here is equal to sigma dash 1, 1, sigma dash 1, 2. And we're looking for the maximum. We're looking for the maximum value for this. So according to the translation formula between the two coordinate systems, sigma prime is equal to Q sigma Q transpose. Sigma prime then will have the following form: sigma 1 cosine squared plus sigma 2 sine squared. Sigma 2 minus sigma 1 cosine multiplied by sine. Sigma 2 minus sigma 1 cosine multiplied by sine. Sigma 2 cosine squared plus sigma 1 sine squared. And the question is, what is theta? because the only variable is theta. I don't know what this orientation is. What is this orientation? So that this value is maximum. So what is theta? Such that sigma 1, 2 prime is max. To find this orientation, differentiate with respect to theta. So sigma prime 1, 2 is equal to sigma 2 minus sigma 1 cosine theta sine theta d sigma dash 1, 2 by d theta is equal to sigma 2 minus sigma 1 d cosine theta by d theta multiplied by sine theta plus cosine theta d sine theta by d theta. If you equate this to 0, you'll find that sigma dash 1, 2 is obtained when theta equal multiples of 45 degrees. And in this case, when theta is equal to 45 degrees, you'll find that sigma prime in this case is equal to sigma 1 multiplied by cosine 45 squared plus sigma 2 sine 45 squared sigma 2 minus sigma 1 cosine 45 sine 45. This is sigma 1 cosine 45 squared plus sigma 2 sine 45 squared, which finally is equal to the average of sigma 1 plus sigma 2 and the difference divided by 2. And therefore, the maximum shear stress is in fact the difference between the principal stresses divided by 2. So let's go back to the definition of the maximum shear stress. It's indeed defined as the maximum difference between the principal stresses divided by 2. Okay, the remaining part in this section is to give 2 examples for which we're trying to find the orientation of the maximum shear stress. Now, you've studied how to do this using the Morse circle before, but I'm just presenting it to you using matrices, which is probably, for me, this is more straightforward. So in a general coordinate system, we have the stress described by the following matrix: 29, 72, 72, 71. Let's see what that means. I have E1. Or I have a general coordinate system described by the stress at the point is described by those numbers: 29, 72, 72, and 71, and we're just looking at R2 and ignoring the third direction. In this case, sigma is equal to 29, 71, 72, 72, and I'm using this coordinate system E1, E2. In order to find the orientation of the maximum shear stress, the first thing I have to do is find the orientation of the principal stresses. So the first thing we have to do is find eigensystem of sigma, and I will show you how to do this using Mathematica in a later tutorial. So we realize when you do this calculation that the eigenvalues are oriented by the angle (53.3 degrees), and in this coordinate system the stress matrix is diagonal, and this value is 125. This is 0, this is 0, and this value is negative 25. And in this coordinate system, sigma prime is equal to 125, 0, 0, negative 25. And the orientation between here and here, or that translation between here and here, is described by Q, where Q is made out of eigenvalue 1 and eigenvalue 2. From this orientation, we can move to the orientation of the maximum shear stress. It's obtained by rotating the these coordinates another 45 degrees. So I'm going to call this E1 or E-1, E-2, where this angle is 53 degrees. Plus 45 degrees. Just going to make these a little bit smaller. E-1 and E-2. And in this case, Q2 is equal to cosine 45, sine 45, negative sine 45, cosine 45, and sigma 2 will be equal to Q sigma prime Q transpose Q2. And using this formula, you are able to calculate the stresses in the new coordinate system, which will be equal to 50, negative 75, negative 75, 50. And you can, between any two coordinate systems, you have a formula. So sigma prime is equal to Q sigma Q transpose. Sigma 2 is equal to Q2 sigma prime Q2 transpose, or Q2 Q sigma prime Q2Q all transpose. And notice that to jump from this coordinate system to the principal stresses coordinate system, I'm multiplying by Q. To jump from the principal stresses directions coordinate system to the maximum shear stress direction, I multiply by Q2. But to jump from the original coordinate system to the new coordinate system, you're multiplying by Q2 multiplied by Q. This is very important. The order of multiplication of matrices is very important, because you first, when you put any vector here, you first multiply by Q and then you multiply by Q2. And since vector multiplication happens, so this is QV. When you first, V belongs to R2. To change its coordinates, you first multiply by QV. Then to change the coordinates again, you multiply by Q2. So see, the order of multiplication is very important. So this is it for the stress measures. In the next section, we're going to use those stress measures to define failure criteria for different materials, in particular for metals.